Well, hello everyone. Welcome to our project Prime Walk to Infinity in 02. And we are the research group in Polymath REU. And today two of us, Daniel Sarnecki and Ben Chen-Li, will be presenting. Our project is advised by Professor Stephen J. Miller, tutor employed. So first of all, let us start with a simple question. Can one walk to infinity with bounded steps on real line just using primes? Well, the simple answer is no, because all we need to do is pick a prime p such that p is larger than capital M if we want a gap of length n between primes. Then the p primorial plus 2, p primorial plus 3, up to p primorial plus p are n-1 consecutive composite numbers. And where p primorial means the product of all primes less than or equal to p. Well, since primorial is defined this way, then 2, 3, and all the natural integers between 2 and p are have a cofactor with p primorial. So that's why they're composite. And well, so now what if we consider Gaussian primes instead of just the integer ring? What if we consider prime walk in primes using primes in Zi? Or Zi is a set of integers, a set of elements of the form a plus bi, where a and b are both integers. Well, the figure below shows all the Gaussian primes of norm less than 1000. We can see that the primes in the graph have a eightfold symmetry, right? And they are all tends to cluster along the near the origin. And well, this actually is a very famous and solved problem called the Gaussian mode problem. And the Gaussian primes are, as we defined before, are prime elements of Zi, and the number of Gaussian primes in a disk of radius n has the order n squared over natural log n. And remember that the prime number theorem tells us that the number of primes between 1 and n is about n over natural log n. So there's much more primes in Zi. And well, actually, there the theorem says a mode of width 6 will exist in Zi. So this is equivalent to say that it's impossible to walk to infinity with step size 6 in Zi. And it's also widely believed that we cannot walk to infinity with any bounded step size. Well, so we start to think about if we can make it in Zi, well, can we do it in 0 to n for any integer n? Well, a simple observation would be that for negative m, the ring has only finitely many units like Zi. But if m is positive, then the ring would have infinitely many units, just like the case in 0, 2, where any power of 1 plus root 2 is the unit. So the number of prime elements would differ a lot, since any prime elements multiplied by units is also prime. Well, because the number of primes is much larger in 0 and for positive n, we conjecture that it's more possible to have a prime walk in these positive quadratic integer rings. We start with the easiest one, 0, 2. So below is some definitions of elements in this ring. The norm of an element a plus root 2b is a squared minus 2b squared. And two elements are called associates if they have the same norm. And we also define standard prime as the following forms with minimal Euclidean norm, or the square root 2 is standard prime, and any element such that its norm is a real prime congruent to 1 or 7 modulo 8 is also standard prime, and any element such that b is 0 and a is a real prime congruent to 3 or 5 modulo 8 is also standard prime in this definition. And well, using this definition, we can see that any actually primes in 0, 2 are just these standard primes with associates. And besides, we also need to notice that the primes in this definition has a fourfold symmetry. So if a plus root 2b is a prime, then a minus root 2b or minus a plus root 2b are also primes. Next, we try to compare a number of primes in a disk of radius n between Zi and 0, 2. The blue point here shows the case in 0, 2, and the red point shows the number of primes in Zi. And we can see that as n gets larger, from 10 to 60 or even larger, the gap or the difference between the number of primes also gets larger. So therefore, it means primes goes faster in 0, 2, and this fact motivates us to study prime walking in this ring. And we also use Mathematica to visualize our standard primes. Here we make each prime of the form a plus root 2b as a dot in R2. And the figure below shows all the standard primes for x, y less than or equal to 800. As we can see here, they're very dense in this region, but they're much denser along the line x minus root 2 y equals 0, which is just the asymptote of the norm function x squared minus 2y squared. So yeah, next Daniel will talk about the conjecture.
So this leads us to our conjecture, which is that there exists some finite step size k such that there exists an unbounded walk along the primes in z square root 2, where for all steps, we are getting further away from the origin, where we denote further away by using the Euclidean distance. So we have two different approaches that we are looking at. One is the random model, where we calculate the probability of integer in z square root 2 being prime. And we use this to generate walks. Then we have the exhaustive mote finding technique, which is used for Gaussian primes. So the idea for the random model is we compute an estimate for the probability a given point is prime based on its norm. Then we use this estimate to build a greedy model that approximates an average walk. This should allow us to then look at the long-term behavior of walks when it becomes too computationally expensive to generate all walks. So first we estimate the number of primes in order to calculate this probability. We consider primes in the region, the absolute value of a squared minus 2b squared is less than or equal to r squared, which is this region you could see below. The green region is for a larger constant of r, and then the blue region is for a smaller constant of r, I think 1. And then the red line that you see going through the origin is the asymptote. Now, note that this is a generalization of the disk region for Gaussian primes, but now we're using the norm of z square root 2. This necessarily means that the region is unbounded as it approaches the asymptotes, unlike the Gaussian norm region, which is just a disk, which is bounded. So we look at the prime number theorem to calculate the number of primes. For ordinary primes, the prime number theorem says that if we consider the interval from 1 to n, we'll have about n divided by log n primes. Using the connection between ordinary primes and primes in z square root 2, we are able to generalize pnt to the ring z square root 2. And this says that the number of primes in z square root 2 within the region we talked about is about this number you see right here. Now, by comparison, the prime number theorem applied to the Gaussian integers says that the number of Gaussian primes in the disk of radius r about the origin is this number you see right here. Now note that these numbers for z square root 2 and the Gaussian integers, they have the same growth. However, the region that these primes are contained in for Gaussian primes is bounded, whereas in z square root 2, it's an unbounded region with infinite area. So for a second, we look at this question of how many primes there are in a circle C of radius r in the first quadrant for Gaussian integers, because this is helpful when we're doing our walks. The Gauss circle problem helps us out here. It says that there are about pi r squared total lattice points inside a circle of radius r. This is a good enough estimate for us. We can estimate the expected value by assuming each point in an annulus between circles of radius d plus r and d minus r has about the same probability of being prime. Then we have our estimate that if C is centered d from the origin, our estimate is this number you see right here. To calculate this number, we just use the prime number theorem for Gaussian integers, and then we found a probability and then just did a simple expected value multiplication in order to get this number right here. So next, in order to make sense of the number of primes that we found, we look at the total number of integers inside this region that we were talking about for z square root 2. We would like to count families of infinite solutions that have the same magnitude as those we previously counted. That way, if we're dividing two infinite numbers, we'll still get a probability. As before, any solution or prime z that we have belongs to a family of solutions or primes that are the associates when we multiply by any power of 1 plus the square root of 2, because these maintain the norm. We can find these families of solutions by considering the equation a squared minus 2b squared equals c for each integer c with absolute value less than or equal to r squared. This theorem of Bernays helps us answer this question. So if we have an integer a function defined on the integers